So here I am within Keysight's advanced battery test and emulation software solution. You can see I have an E36731A battery emulator and profiler connected to the software. You can also connect a DAC. In the demo, I will go into more detail on how you can use this functionality. With the software, you can emulate a battery, profile a battery, discharge a battery to perform a battery rundown test, and cycle a battery. I will start in profiler mode. So here I am in profiler mode. In profiler mode, you can create a battery model based on an actual physical battery. You can do this by either discharging or charging the battery. I will discharge the battery. You can discharge the battery using constant current, constant power, constant resistance, or you can use a dynamic waveform. So I've already loaded this dynamic waveform that I generated. So it mimics the behavior of the device. So here you can see the device taking measurements and then connecting to a Wi-Fi network. I have increased the current amplitude by multiple to speed up the process. Batteries do have lower capacity at higher C rates, so it won't mimic the battery behavior perfectly. However, using a dynamic waveform will generate a much more accurate model that better represents the battery behavior than using a generic model from a manufacturer or just using constant current drain. The software will repeat this waveform over and over again until the batteries run out of capacity and the profile has been created. So another key feature of our solution that I would like to highlight is the ability to tie a battery model to a temperature. You can either manually input this or pull it from a DAC. Think of the articles you may have read about the challenges EVs face in cold weather. Same applies to IoT. Cold weather can impact battery life. And with our solution, you will have a known good reference for testing at cold temps versus having to use a temperature chamber every time. Think of the time savings of this. So I now have a CR123A battery connected to the E36731A, so I can go ahead and start profiling. So let me hit start. So here you can see the hardware pulse the battery to measure its internal resistance. So now the hardware starts to mimic the behavior of the device. And the software will map out the open circuit voltage and the internal resistance of the battery versus state of charge. Let me go ahead and skip ahead here a little bit. So here you can see the software starting to map out the open circuit voltage and the internal resistance of the battery versus the state of charge. This will take some time, but you will see a completed profile when we go to emulate mode, which we'll go to next. So here we are in emulation mode. I've already loaded a battery model that I previously created in Profiler. You can see the open circuit voltage and the internal resistance of the battery vary greatly with the state of charge. The great thing about an emulated battery is it provides you with a known good reference. With physical batteries, you cannot always have complete confidence that your test results are repeatable. So for example, battery characteristics can vary between batches. It is critical that your tests be comparable and repeatable. An emulated battery provides you with this. Also think of the challenge of testing at a particular charge level with a physical battery. You have to precisely discharge to that level, versus with an emulated battery, you can instantly switch to that charge level. Also, let's say you were to cycle a battery 100 times. Then you could capture that battery model in Profiler, and now you have a known good reference for an aged battery. With physical batteries, you have to worry about losing the battery, or what if it was aged without your knowledge? So now let me change the state of charge to 75%. And here you can see the state of charge change instantly. So now let me go ahead and start emulation. So there you could hear the CO2 smoke detector turn on. You can see the LED flashing as it initializes, and you can see the software tracking the voltage and the current draw of the device. So now let me go ahead and skip ahead here. So I've now stopped battery emulation. Here you can see the device transition from being an initialization phase into a lower power phase, where it's taking measurements and attempting to connect to the Wi-Fi network. So now let me zoom in on the current drain. So here you can see the device drains around 28 milliamps when it attempts to connect to the Wi-Fi network. And now let me zoom in on individual current measurements of the combination CO2 and smoke detector. So for measurement A, the device drains around 1.6 milliamps. And for measurement B, it's drawing in the microamp range. And this really shows you the wide dynamic current measurement range of the E36731A. And you can see how the combination software plus hardware tool is a great way to identify ways to extend battery life. So for example, you could compare hardware version A versus hardware version B, or software version A versus software version B, and identify which version draws less current. The software tracks the overall depleted capacity, plus you can zoom in on individual current drain events. Again, this is a great way to identify ways to extend battery life. So another thing I like to highlight about battery emulation is that it's a great way to increase your confidence levels in your overall battery rundown estimate. A chief challenge to creating this calculation is that battery characteristics can vary greatly with the state of charge. So with battery emulation, you can quickly calculate the current drain at 95%, 90%, 85%, and so on. You can use these data points to greatly enhance your confidence level in your calculation, right? This type of calculation is particularly useful for devices like a smoke detector where the steady state waveform is repetitive. However, for a device like a smart vacuum, which has a much shorter battery rundown time and the waveform is not repetitive and highly dependent on usage, then using the discharge mode is a much better method. And now let's go to that next. So here I am in discharge charge mode. You can discharge a battery and track the consumed capacity, or you can charge a battery and track the charge capacity. In this demo, I will discharge a battery. You can discharge the battery using constant current, constant power, or constant resistance, or utilize a dynamic waveform. So I've already created and loaded this waveform. So this waveform just represents a generic IoT device that's transitioning between power states, and you can see it connecting to a Wi-Fi network on a regular basis. And I've clicked continuous, so this waveform is just repeated. I have a lithium-ion battery attached to the E36731A, so we can go ahead and click start. So here you can see the electronic load start to emulate the behavior of the device. So here it is emulating and connecting to the Wi-Fi network, and you can see the software is tracking the consumed capacity over the time. This battery rundown test will last until the battery is out of capacity or the cutoff voltage is reached. You can see this is a great way to develop an estimate for the battery runtime of your device. So let me go ahead and click stop, and let's switch over to cycler mode. So here I am in cycler mode. In cycler mode, you can charge and discharge a battery repeatedly to identify battery aging effects. You can repeat a cycle up to 1,000 times. I've already loaded a battery cycle pattern. So for discharging, I will use the same waveform I utilized in discharge mode, and I will charge the battery utilizing constant current. So I have my lithium-ion battery here attached to the E36731A. So I can go ahead and click start. So here you can see the electronic load again start to emulate the behavior of the device, and you can see the software track the depleted capacity of the battery. This will take a long time, so let me go ahead and click stop and switch over to a completed cycler operation. So here is a completed battery cycler operation. You can see that I cycled the battery 5 times. For this operation, I utilize constant current to discharge and charge the battery. You can see the software tracks the amount of time it takes to discharge and charge the battery for each cycle. Anyone who owns a smartphone knows that battery runtime can decrease as you cycle a battery. And this can apply to any IoT device that utilizes a rechargeable battery. Therefore, it is critical in many cases to really understand this effect. So that completes our demo. We've gone through how to profile a battery, emulate a battery, run a battery rundown test utilizing discharge mode, and cycle a battery. You can use these capabilities to extend and validate the battery runtime of your IoT device and also better understand battery aging effects.